Right.
Okay, John, your electrifying presentation.
All right. Okay. Well, not a lot of people to introduce myself to, but I guess I will anyway. I'm John Sullivan, call sign KG7WFQ. I'm in Mukilteo, Washington, and I'm an amateur extra class ham. I haven't been that ham all that long. I was licensed initially in 2015. I'm also a VE for both ARRL and GLARG. And we're going to be talking today about electrical principles. And there's a bunch of subtopics involved in this. I'm not going to take the questions in the order they are in the question pool. Instead I've grouped them together so that their common topics are all together, so it kind of flows a little more logically, because the question pool is not necessarily in a logical order, but I've kind of juggled it around. So if you're trying to follow in the question pool, it won't be in numerical order. The subtopics include terminology and units, conversion of electrical units, current and voltage, conductors and insulators, series and parallel circuits, alternating and direct current, capacitance and inductance terminology and units, Ohm's law, decibels, calculating power, radio frequencies and definition of units, and impedance definition of units. A lot of topics in this section. Total of 52 questions in the pool. It gets divided into 4 subsections, and there'll be one question from each subsection on the exam. So we'll just get right into it then. First thing I want to talk about is terminology and units and converting units. I'm going to lump all those different kinds of units together in one presentation, part of the presentation here. So let's talk some bit about the characteristics of electricity and some of these definitions. Power. Power is the rate at which energy is consumed. We measure that in watts. When you get your electric bill, that they're measuring how many watts, the rate at which you've consumed the electricity they're selling you. Resistance is opposition to electric current, and it's measured in ohms. Voltage is the measurement of electrical potential or electromotive force, and it's measured in volts. And we'll go in some detail of explaining what all this means in a moment. Current is the flow of electrons, and it's measured in either in amperes, which is usually abbreviated as amps, but amperes are amps. And frequency is the number of cycles per second in a wave, and it's measured in hertz. So some more definitions here you'll see in the test questions. AC is alternating current. A is the abbreviation for amperes, also sometimes abbreviated AMP or amps for amps. Little d capital B is the abbreviation for decibels. Let's talk about that. DC direct current, not District of Columbia, direct current. Electromotive force is sometimes abbreviated, mostly abbreviated E, sometimes EMF. Hertz, capital H, little z, is the cycles per second. I for current. Speaking of hertz again, you either have kilohertz and megahertz, thousands of hertz and millions of hertz. If it's kilohertz, it's a small k. If it's megahertz, it's a big M. P for power, R for resistance, R for radio frequency, V for volts, and ohms, we use the Greek letter omega, which when you're trying to type something up gets to be a bit difficult, but ohms. Quick chart here, which is probably a good thing to kind of use to remember all of this. You know, power is watts, resistance is ohms, voltage is volts, that one's easy. Current is amperes or amps, and frequency is hertz. These are the units of measure that we're going to be concerned about here. We're dealing with metric units, and being as they're metric, they're all referred to in different powers of 10. It's a decimal system. So if you look at, it's a little busy there, but you can see they've got a 0 in the middle. To the left are things that are larger than 1. So 10 to the 0 would be 1. 10 to the first, 10 to the second, and so on. So that would be tens, hundreds, thousands, millions, and billions, or deca, hecto, kilo, mega, and giga. You can see down there in the lower left, we've got 1 hertz. 1,000 of them would be a kilohertz. 1,000,000 hertz would be a megahertz, and 1,000,000,000 hertz would be a gigahertz. Now, if you're going to smaller than 1, we're talking about a tenth of something, 1/100th, 1/100th, 1/1000th, 1/1,000,000th, 1/1,000,000,000th, 1/1,000,000,000,000th. And those terms are deci, centi, milli, micro, nano, and pico. You don't see deci much. You will see centi, milli, micro, nano, and pico, however. So if you had 1 ampere, if you had 1/1000th, it would be a milliampere. 1/1,000,000th, it would be a microampere. A 1/1,000,000,000th would be a nanoampere. Okay, so that's terminology. Let's take a look at the first question we've got here. So what is the name for the flow of electrons in a circuit? And we talked about current flowing, right, in an electric circuit. So that is current. So the flow of electrons is called current. And how do we measure the flow of electrons? Remember, we said that was amperes or amps. Okay. What is the electrical term for the force that causes electron flow? Remember, we said electromotive force was another terminology for voltage. So the answer to that is voltage. You can think about that like pressure or force that's pushing electrons through a circuit. What are the units of electrical resistance? Remember, that's the funny letter, ohms, the Greek letter omega. Which term describes the rate at which electrical energy is used? That's what you get charged for, the rate at which you use energy. That is power. And how do we measure power? We measure it in watts. Now, I'm going to get confused. I see that meter up there that says kilowatt hours. But when you get your bill, they measure how many watts you used over what period of time. But watts is the unit we care about. Watts for power. And then again, the unit of frequency. Frequency is how often something happens, right? How frequent something is. So cycles per second, that would be hertz. All right. Any questions on any of those definitions before we get into the mathematical part of this? All right, so how many milliamperes in 1.5 amps or amperes? Remember, millis are thousandths, so 1,000, 1 ampere would be 1,000 milliamps, right? So 1.5 amps would be 1,500 milliamperes. Which is equal to 1,500,000 hertz. Okay, well, this is a little bit more involved. It's going to be 1,500 kilohertz. You immediately probably thought, oh, mega, million, but you notice it's a big number. So it's 1,500 kilohertz, which would be 1.5 megahertz. Okay. Which is equal to 1 kilovolt. So kilo is for what? Kilo is for thousands. So C would be 1,000 volts. Kilovolt. And what would be equal to a microvolt, right? A microvolt. So micro is a millionth. So it would be a 1/1,000,000th of a volt. So you can see that what you kind of need to know is those terms are fairly significant. There's a number of questions, so the odds of getting one of these is pretty much up there. Which is equal to 500 milliwatts. Okay. Well, we know that 1,000 milliwatts is a watt, right? So that means that 500 would be a half a watt. And what's equal to 3,000 milliamperes? Okay. So a milli is 1,000, right? So 1,000th. So 3,000 milliamperes would be like 3 amps, right? Divided by 1,000. What's equal to 3.525 megahertz? So mega's a million, kilo's 1,000. So you're going to have 3,525 kilohertz would be the same as 3.525 megahertz. You move the decimal point 3 places. Similarly here, again, you see there's a lot of these in the pool, which is equal to 1,000, or I'm sorry, equal to 1,000,000 picofarads. So what would be equal to 1,000,000 picofarads? Well, it's going to be a 1 microfarad. So you can see down there at the bottom, you get a look at the decimal points, the numbers of zeros that are in there. You can see that micro would be 1,000,000. Move that 1 down to the row below, and you would see that it looks like 1,000,000 behind it. So that would be a microfarad. And here we go. What's equal to 28,400 kilohertz? Again, you move the decimal point and you get 28.4 megahertz. Got to be careful looking at these answers because you could see the first answer was 28.4 kilohertz, but no, that should be megahertz. So you got to read these carefully, particularly on the kilo and megahertz, as to which it is. So that's a hint on the test taking. What's equal to 2425 megahertz? So now we're going the other direction. We're going up even higher. Again, move the decimal point 3 places, and you get 2.425 gigahertz. Any questions on the? I know nobody said there was going to be math today, right? Well, there is going to be math. Any questions on this converting these units?
I love math.
Well, good, because you'll get a chance to use it. Although really the good news is that these numbers are, I mean, it's moving decimal places in your head mostly. It's not difficult math, and the numbers that they use almost in any of these questions are going to be, very straightforward numbers that you can usually do in your head. And you can have a calculator for the exam if you want to in scratch paper. So the math isn't difficult math.
Or a slide rule.
I lost my slide rule years ago. I wish I still had it, but that's what I had to use in college. So, all right. So now we're going to move to another some other subtopics of current and voltage, conductors and insulators, series and parallel, and you can read the list there. So a little explanation what we're talking about, how voltage, current, and resistance are related. Electricity only flows if there's a complete circuit. There has to be a route for the electricity to flow through. So here's a quick illustration. On the left, you've got essentially a battery, which is your electromotive force power, your source of energy. It is your voltage. You can see that the solid line is think of that as your wires. It's going to go to a load on the far right, which is your resistance. So you have a route for the electricity to travel around that circuit. You can see that we have down in the bottom right there a current. It says current. That would be an ammeter. So you have this meter there that's going to measure how much current flows through it. And you have another meter up there that's across the two wires. And it's going to measure the difference in potential or the difference in the energy level between one side and the other. So you always measure voltage like that in parallel, and you always measure current in series. You can think about, just remember that voltage and current measurement are going to be opposite. One's going to be series, one's going to be parallel. And current's easy to remember because it has to flow through everything has to flow through the meter for you to measure all of it. So your current is always going to be measured in series, voltage will be in parallel. So as I said, the current's got to flow from one side to the other. So here we have this similar illustration here with a battery going through a light bulb, through circuit goes around, and you've got this switch. As long as that switch is closed, that light's going to be on. But if that circuit is incomplete, there's a break in it, like you open up a switch, then you no longer have current flowing and the light goes out. Basic electrical principle. You can also think about the electricity like water. You can think about how water works. Water flowing through a pipe. So you can see the analogy here of the pump on the left pumps the water through the pipes. You can measure the pressure, the difference between one side of the pump and the other, and you can measure the flow of the water through the pipe. That's similar to electricity, with the pump representing the battery and the pipe representing the wires. And you would measure the voltage with a voltmeter across the battery, across the two sides of the circuit. And you would measure the current through the wire with that amp meter to measure current in series in that circuit, and the voltmeter in parallel. So that's another way of thinking about it, just so you can kind of keep it straight. It's just like that. Continuing with that water analogy, you can see that on the right, you've got a hose. You've got a hose. If the nozzle's closed, even if the faucet's open, there's water pressure in the hose. There's a lot of pressure built up, but it's not going anywhere because it can't. It's blocked. There's not a complete circuit for it, if you will. Similarly, on the left, you can see you've got a lamp plugged into a wall outlet, but the switch is off. The potential is there. The pressure, the electrical pressure or the voltage exists at that outlet, but there's no place for the current to go because the switch is open. Just like with the hose in the lower right, once you open up that nozzle, then there's a place for the water to go and it flows. That pressure that's built up there forces the water out. Similarly, with the current, the voltage or the electromotive force, the electrical pressure, if you will, is released when you turn the switch on, because then you have a complete circuit and the electrons can flow. So that's a way of thinking about it. You'll see up in the upper right there, we talk about E equals, and we're going to get to this later, in fact, in another section, but those are just some formulas we're not going to worry about at the moment. We'll get to those later in the course. Okay. So you have conductors and insulators. In a conductor, the electric current can flow. And without getting into a lot of detail, basically it has to do with the atomic structure of a material, whether it's going to be a conductor or an insulator. A conductor allows electricity to flow, an insulator prevents it from flowing. So a conductor has what are referred to as valence electrons or outer electrons, and those materials have essentially a weak hold on those electrons. Those electrons can move and they strike neighboring electrons, and it causes a motion and a chain reaction that flows over the surface of that conductor. Whereas an insulator, that doesn't happen, so the electricity doesn't flow. Metals are generally good conductors, and non-metals generally are not. That's kind of and we all kind of know that, I think, intuitively. Good conductors: copper, silver, gold, aluminum, platinum, all your metals. Good insulators are things like glass, wood, rubber is very good. Even air is an insulator, plastic. Now, water is also an insulator if it's pure water, but salt water, including the salt water in your cells in your body, is a conductor because of the minerals and things that are in it. those have the free electrons, and therefore current gets conducted. So you are not an insulator. Do not try to act as one with electricity, because you will not survive. Let's talk about, again, a little bit more about parallel versus series circuits. We mentioned about testing, putting meters in parallel or in series. Well, the same concept with how a load on a circuit is. Looking at the lower right, you can see here's a load in series. You've got two, in this case, lamps, let's say. They are in series. The current flows into one, out of it, and into the next one. There's one path and one path only, and it goes through both of the loads. On the other hand, on the upper illustration, the loads in parallel, you can see that the circuit splits. So there's two paths for the current to flow. It can go through the first load, or it can go through the second load, or go through both of them at the same time. So if one of them is removed, the current would still flow through the other one. Whereas if you remove one of the items in series, you have an open circuit and nothing flows. This is an illustration of the same thing with 3 light bulbs here. These are in series. Current has to flow through each light bulb in turn. Whereas with a parallel circuit, it splits off, and it'll go through all 3 of them simultaneously, if you will. And if any one is removed, there's still an alternative path for the current. So this is like your Christmas tree lights, the old cheap kind that are in series. One light bulb burns out, they're all out. You don't know which one's the bad one. You got to replace them all to figure it out. That is a series circuit. A parallel circuit, one light burns out, the others keep going. So that's your difference between a series and a parallel circuit. Let's talk a little bit about DC and AC current. Direct current flows only in one direction. Example of that would be battery-operated devices. That's direct current, like a flashlight or whatever, or your car battery. AC current flows in both directions. Voltage and current vary with time. We'll see another illustration, but that's what creates a wave on the right, your alternating current wave. So think about it like this. Remember we were talking about the water. Direct current, the water only flows, or the current only flows in one direction from the pump or the source. So the waterfall, the water comes down, it doesn't go back up. So you can think about, you got a pump, it pushes the water in one direction only. That's direct current. Alternating current's a little bit different. With alternating current, think about it as that kind of funky little pump they got there that if you pull up, it pushes the water up through the pipe. If you push down, it's pushing the water down through the other pipe. So it would go back and forth, back and forth. That's alternating current. And that would be like the waves in an ocean as opposed to a waterfall. The waves come in, they go out. They come in, they go out. Okay? Alternating current. Another illustration here, your alternating current, or your direct current, I'm sorry, on the left flows in the one direction. Your alternating current, as you can see, alternates. The voltage and the current increase and decrease and creates that sine wave. That's alternating current. A couple more definitions that are important with alternating current. Capacitance, that's the ability to store energy in an electric field. And that capacitance is measured in farads. These are all named after scientists, a farad. Inductance, that's the ability to store energy in a magnetic field, and the unit is Henry. So capacitance is electric field, inductance is magnetic field. Impedance is opposition to the current flow in an alternating current circuit. So it's like resistance, but this impedance is only in an AC circuit. And its unit, just like resistance, is the ohm, Greek letter omega. Any questions before we get into the question pool portion? All right, well, let's take a look at some of these questions. Why are metals generally good conductors of electricity? Remember we talked about how those electrons bump into each other and move around? That's because good conductors have many free electrons. Which of the following was a good electrical insulator? Not a conductor, an insulator. Well, 3 of those are metals. And we've said that metals are good conductors. So that only leaves glass as your insulator. And glass is a good insulator. Which type of circuit is DC current the same throughout all components? Okay, is the current the same throughout all the components? Okay, well, that's going to be your series circuit because the current flows through all of them, one after the other. It's the same. The current doesn't split up into multiple paths. It's the same through all of them. In which type of circuit is voltage the same across all components? Well, as you might guess, it would be the opposite, the parallel circuit. The voltage is going to be the same, but the current will not be. The current will depend on what the load is that it's going through. Okay. Which of the following describes alternating current? Well, it alternates, right? Okay. And it can't be all of these answers. Oops, I should say all of these answers are correct. Oops. Because they're not, it can't be both positive and negative at the same time. So the answer is current that alternates between positive and negative directions. You get a complete wave. It's just not half a wave that goes just up and back to 0. But if you remember that illustration of the wave, there was a positive component and a negative component. Current that alternates between positive and negative directions. What describes the number of times per second that an alternating current makes a complete cycle? Well, that's how frequently it changes, right? So that is a frequency. The higher the frequency, the more wave changes there are. The lower the frequency, the fewer ones. What type of current flow is opposed by resistance? We didn't really talk a lot about this, but the answer is all of these are true. Remember I said that impedance is resistance, but only in AC circuits, but you also have resistance in AC circuits or DC circuits, and also resistance to RF energy. What describes the ability to store energy in an electric field? Remember, we talked electric fields and magnetic fields. Electric field is capacitance. What is the unit of capacitance? Again, these are things you're just going to have to memorize, but we know that it's not ohms, that's resistance. We know it's not volts, that's current, that's electromotive force. So it's either the Henry or the farad, and the capacitance, it's the farad. So we talked about ability to store in an electric field was capacitance. What about a magnetic field? Well, it's going to be the other one, inductance. Okay. And the unit of inductance, we've never talked about a coulomb. We know that ohm is resistance, and we already found out that farad is capacitance. So that leaves the Henry for inductance. All right. Any questions before we move on to the next subset? Okay, we're going to talk about Ohm's law. Ohm's law is an important concept. We're going to talk briefly about decibels, and we're going to talk about calculating power. Okay, Ohm's law. This is again the interrelationship between voltage, current, and resistance. This circle is a handy thing to memorize. I'd suggest that you might, along with a couple other circles, we'll talk about that you would memorize these circles. And maybe during your exam, if you have your scratch paper after the exam starts, the first thing you might want to do is draw these circles on your piece of paper so you have them for reference. You can do that during the test. Can't bring it in, but you can write it down once the test starts. Okay. We talk about unit is volts. symbol is V, and we measure it across or parallel to the load. Current is in amps or amperes, symbol is an A, measured in line, resistance is ohms, omega. So E is voltage, and you've got I and R. E equals I times R. If you were to put your thumb over the E, you would see you have I and R next to each other. You could multiply them together. That gives you E. If you put your thumb over the R, you want to find resistance, put your thumb over the R, you see you have E over I. That means you divide voltage by current. If you want to find current, I, you put your thumb over the I, and you can see the E above the R. E is divided by R. So you divide voltage by resistance, and it will give you current. That's why I say that's a very handy tool to use. Decibels. Decibel is a unit for expressing the ratio between two physical quantities, and it's a logarithmic measurement. A decibel is a tenth of a bell, decibel, right? It's a logarithm. It's simply the reciprocal of a power of 10 function. And we don't need to get into the math of this. It's very simple rules to remember. That what you need to know for the test is pretty basic. And that is, it's a logarithmic curve. You need to know that if you double something, it increases by 3 dB. If you have something, it HALF, if you have half of something, it's minus 3 dB. And the dBs add together to double. So if you double something, it's 3 dB. 3 and 3 is 6. That would be quadrupling, be 4 times. 10 dB is 10 times. The ones you need to know are 3, 6, and 10. That's all it'll be on the test. 3 is doubling, 4 is quadrupling, and 10 is 10 times, or a half, or a fourth, or a tenth if it's going minus. That's all you need to know about decibels for the exam. And here's the example. You can see plus 3 is doubling, plus 6 is quadrupling, plus 10 is 10 times. Minus 3 is a half, minus 6 is a quarter, minus 10 is a tenth. That's all you need to know for the exam. Okay. Watt's law, we talked about Ohm's law, which was the relationship between voltage, current, and resistance. Watt's law is the relationship between power, current, and voltage. Potential or electromotive force or voltage, E, again, same letter symbol. Current, electron flow, same thing, I. Now we have a P for power. So pi, we're looking at, you can remember that cherry pie there to remember it. So you put the P over the I and the E and draw that same circle, and you use it the same way. If you want to find P, you put your thumb over the P, and you'll see that it's I times E. If you want to find E or the voltage, you put your thumb over the E, and you see that you have P above I, so you divide power by current. If you want to find current, put your thumb over the I, and you see you have a P over an I, you divide power by voltage. So that's the handy tool for remembering that. So that's your ohms and power calculations. Those two symbols, or two diagrams, if you will, are the best way to remember these for the exam. Now you could do that option, those two circles, or you could memorize the one on the right, which gives you all the various combinations. Which one would you really prefer to memorize? I think those two circles on the left are going to be the answer for you. All righty, get into the question pool. Before we do that, any questions so far? All right, moving on. What formula is used to calculate current in a circuit? In a circuit. All right, I'm going to walk through this for you. So those are the options, right? The answer is going to be I equals E divided by R, because again, we look at that circle, we're trying to find I, we put our thumb over the I, we see it's E divided by R. So current equals voltage divided by resistance. So what is the formula used to calculate voltage in a circuit? Okay, remember, E is on the top, I and R are on the bottom, so it's going to be E equals I times R. What formula is used to calculate resistance in a circuit? So they get you all three directions on this question. So again, we got R. Remember, it's on the lower right of that circle. You're going to have an E over an I, right? So it's going to be E divided by I, volts divided by current, by amps. So practical application of this is going to be, what is the resistance of a circuit in which a current of 3 amps flows when connected to 90 volts? So the numbers are always going to be simple numbers like this, okay? All right. So again, the resistance of a circuit, you're trying to find the resistance. So you're going to put your thumb over the R. You get 90 volts on the top, and you got 3 amps on the bottom. So you're going to divide the 90 volts by the 3 amps, and that's going to give you 30 ohms, which was answer B, 30 ohms. So what's the resistance in a circuit for which the applied voltage is 12 volts and the current flow is 1.5 amps? Okay, the answer is going to be 8 ohms. How do we get to that? Well, again, put your thumb over the R for resistance, because that's what you're trying to find. You've got the 12 volts and 1.5 amps. You divide 12 by 1.5 and you get 8 ohms. What's the resistance in a circuit for which the applied voltage? Oh, I went the wrong way there. Sorry. What is the resistance of a circuit that draws 4 amps from a 12-volt source? Again, looking for resistance. Thumb over the R. We got 12 volts and a 4 amp source. 3 ohms is the answer. Now, these are all, there's a lot of the same thing here you're seeing, but that means there's a lot of these questions in the pool, so the odds of getting one of them is much higher. What's the current in a circuit with an applied voltage of 120 volts and a resistance of 80 ohms? This time we're looking for current, right? So we're going to put our thumb over the I, and we're going to have that. Let me do that. Over the amps current, we're going to have 120 volts over 80 ohms. That comes out to be 1.5 amps. That's the answer. What's the current? Again, we're looking for current through a 100 ohm resistor connected across 200 volts. And that's going to be 2 amps. 200 divided by 100. What's the current through a 24 ohm resistor connected to 240 volts? Okay, so volts divided by ohms, right? So we're going to end up with 10 amps, right? 10 amps. What's the voltage? So now we're looking for voltage across a 2 ohm resistor if a current of 0.5 amp flows through it. Same idea. This time the thumb goes over the E. We've got resistance times current, or 2 times 0.5, or 1 volt. What's the voltage across a 10 ohm resistor if 1 amp current flows through it? Same deal. Multiply them together, you get 10 volts. That's the answer. We're having so much fun with this, we'll do another one. What's the voltage across a 10 ohm resistor with 2 amps flow through it? Again, voltage is current times resistance, 2 times 10, 20 volts, same deal. Now, a little shifting gears slightly here. Which decibel value most closely represents a power increase from 5 watts to 10 watts? So we've gone from 5 to 10. So we have doubled the wattage, correct? So remember, you need to know 3 decibel numbers, 3, 6, and 10. 3 is a doubling, 6 is a quadrupling, 10 is 10 times. So since it doubled, it's going to be a 3 dB change. Which decibel value most closely represents a power decrease from 12 watts to 3 watts? Okay, so 12 to 3. So that's not half, that's a fourth, right? So that would be a minus 6 dB. Each halving is 3 dBs. So you have 2 halvings, 3 and 3 is 6. Okay. Which decibel value represents a power increase from 20 watts to 200 watts? So we haven't doubled or quadrupled in this case. We have the power increases 10 times. That's going to be 10 dB. That one's easy to remember. 10 times is 10 dB. Easy to remember. Now we're talking about power. So what is the formula used to calculate electrical power in a DC circuit? Remember the pi, and the P was on top, so P equals I times E. P equals I times E. You have your pie chart, so to speak. All right. How much power is delivered by a voltage? Oh, that's a typo in there somewhere. 13.8 volts DC and a current of 10 amps. So P times I equals I times E, right? So it's going to be 13.8 times 10, right? Put your thumb over that. 138 watts. How much power is delivered by a voltage of 12 volts and a current of 2.5 amps? Once again, you're going to multiply 12 times 2.5, right? Looking for P, you get I times E, 12 times 2.5, going to be 30 watts. How much current is required to deliver 120 watts at a voltage of 12 volts DC? Well, again, oops. We're going to go back to our chart. We got 120 watts. We've got 12 volts and we want to find I. So we're going to put our thumb over the I. We're going to divide 120 by 12 and we're going to have 10 amps for the answer. Okay, any questions on that? You can be pretty sure you're going to have at least one question about all of that. Okay. I'm going to talk about some radio frequencies, definition in units, and impedance definition in units. What does the abbreviation RF mean? We talked about that at the very beginning. That is radio frequency, signals of all types, radio frequency. It's not resonant frequency, it's not real, it's not reflective, it's radio frequencies. What is the abbreviation for megahertz? This is where you got to keep your capital and lowercase letters straight. It is capital M, capital H, little z, megahertz. It's the abbreviation for kilohertz. It is not A. Remember I mentioned that there's a difference between the mega and the kilo. The kilo is a small k, so it's D, kilohertz. What is an impedance? We talked about that. That was unique to AC current, and it's a type of resistance. It's opposition to AC current flow. It's not the inverse of resistance. It's a kind of resistance. We've never talked about a Q or anything else, and the answer is simply opposition to AC current flow. And finally, what is the unit of impedance? Remember, it's a kind of resistance to AC current. Same measurement as resistance. It is the ohm. All right. Any questions on anything? Is anyone still awake?
Hey, Emery, how are you doing on this material?
Doing really good. I really enjoyed that presentation, John. I really liked the way that you grouped the questions that went together more so than going them in chronological order. It made it really easy to follow. So thank you for doing that.
Yeah, I really think that you've got to do that because the question pool, you've got this stuff interspersed and it's confusing unless
Yeah.
you really got to, they don't think about that when they put the pool together. They don't care about any of that. But if you want to try and learn it, you got to kind of group it logically.
Yeah. So thank you again. I
No,
really
you bet.
appreciate you doing
You
that.
bet.
Hey, Leo, I know you're driving. How are you doing on the material?
It puts quantum computing into more perspective.
Okay, that was breaking up a little bit. I think you said put it in perspective.
Yeah, quantum computing.
Okay,
Yep. I've been kind of reading about it. It really puts that a lot more into perspective. And, when it uses, semiconductor to, process data and in space and three different points in space at the same time, it's pretty amazing.
yeah, if you're used to the terminology in other applications, it makes it a lot easier.
Yeah, the real
no. And I love math. So everything is like all this stuff makes sense. Just listening to it, I could totally process everything in my head, even though I didn't. I'll go back and look at the presentation because seeing it will be amazing. So,
Yeah.
but yeah,
Well, kind of a couple of the takeaways from this are, yeah, you can take a calculator and everything, but the numbers are pretty simple numbers for the exam questions. It's you don't need your slide rule or your calculator for the most part, but have it there for comfort. That's great. But memorize those two circles, the P equals IE and the E equals IR. Memorize those circles and you can't go wrong on any of those answers. And the other thing is you just kind of have to memorize some of the terminology, the hertz and farads and that sort of thing. And that's this whole part of the question pool. That's the bulk of it. And then the concept of series and parallel and how that water illustration is a good way to kind of keep all of that stuff together in your head, I think. So hopefully that helps.
well, and I got some electrical work to do in the cabin, and so this will help out tremendously with that, and then also looking at doing solar, and so this is like gold for understanding then what your power needs are.
Exactly. Yeah. This has a lot of application in day-to-day life when you're doing things. Yeah, it's good stuff to know.
So one of the, well, first of all, I'm gonna stop the recording.